One of the first tasks we're going to look at this week is to revisit the pendulum waves experience. I hope you enjoyed that video, by the way. It's always interesting to me to see the beautiful patterns that can come up from very simple explanations. Now, the task you were originally given in class was to identify all of the variables that you think could possibly have been a factor. And when we're doing a task like this initial brainstorming is very important. In mathematical modeling, you want to make sure that you've identified each of the potential items you might be interested in. And so it's important that we don't stifle that flow of ideas up front. So I really encourage you to come up with everything, even if it might not be something that would be initially obvious. So the first step in mathematical modeling then is to identify all of these variables. And what I'm hoping you noticed is that the variables themselves were things that had a number you could attach to them. For example, the weight of the balls, the temperature of the room, the volume of the music. All of these are items that could be measured. And it's important in modeling to realize that if something cannot be measured, we can't really use it as a variable. Yes, it might be something that could be important, but it's not something that we can measure. So for example, this is way out there, but let's say that we really had magic and we could push those balls magically. Well, we can't measure that. And since we can't measure it, it's not really a variable that we can identify. I hope none of you thought that that was the case. I don't think anyone did, but just to be on the safe side. So in order to be a good variable, it has to be something that is measurable. That's a key part of mathematical modeling. So you've done the first phase now in terms of identifying variables. Our first task today now is the second part, and that's to prune those variables down to what is the most logical or the most concise explanation. And there's an old adage in mathematics and science and philosophy in general that states that the simplest explanation is the best. In this case, the explanation that requires the fewest number of measurable variables. You probably have heard this in terms of Occam's razor. You know, the simplest explanation is the one that's most likely to be correct. So our task now is going to be to try to identify what the simplest explanation in terms of the fewest number of variables there might be that would explain the phenomena that we saw. And it turns out that there's a single variable that'll account for almost everything that we observe. Let's see if we can make sense of that together. If we take a look right now at this formula is the formula for universal gravitation. And it is the case that by far and away, the single most powerful thing that we see that's taking place here has to do with the force of gravity. Gravity is acting on these balls in such a way as to cause them to move. It literally is the only force that is acting upon those little balls. And so let's see what this tells us. Well, when we initially look at something like this, it can almost be overwhelming. It's like, oh my goodness, there's so much here that we don't know. And in order to truly understand something, we need to be able to read that just like we would read a story in a textbook. So let's see if we can read what this is saying. F sub g, that means the force due to gravity, is equal to something g. Well, what is g? Well, it turns out g is a constant. And remember we talked about variables and constants. Well, this is just a number. It's a force. It's a constant that we can't change. So it's not a variable. This is the universal constant of gravitation. And that means that wherever in the universe you are, this will be the number. It's something we have no control over. So that's kind of a nice thing. Basically, it's just a number that's out there. It's kind of an ugly looking number, I guess, if you don't like decimals and if you don't like exponents, but it's a nice number. And So it's equal to this number, and it's times something. Well, times what? Well, times the mass of one thing and the mass of the other thing. Well, what are the masses that we are talking about here? Well, we have the masses of the little ball, and then we have the mass of the Earth. And I'm going to show the mass of the Earth a little more accurately in terms of making it look like a circle here. Let's just go ahead and we'll draw the circle. And the tool that I'm using for this is called a compass, if you don't remember that. Compasses are an important tool that we use in geometry. So, you know, if you haven't used a compass for a while, you may want to practice a little bit as we think our way through this. And so we have two radiuses involved. We have the radius from the center of the Earth, because that's what we're looking at here, is this radius squared. And we have these two masses. So we have the mass of the little ball, that's M1, and then we have the mass of the Earth, and that's M2. So the only thing that's going to change in this one is we could change the mass of the little ball. We can't change the mass of the Earth, though, so I'm going to put a check by this. That means that's one more thing that's out of our control that we don't have to worry about. So the mass of the Earth is not a variable, it's a constant, isn't it? And I hope you're seeing how these terms, in terms of constant and variable, can be used very well for us. Now, as we go forward from here, what we'll see is we'll see what's left that we can change. Well, we could change the mass of the little ball. That is something that's in our power, so that's a variable. So let's think for a second. The mass of the Earth compared to the mass of the little ball is just so much larger that it's not even funny. I mean, you think about it, it's literally hundreds and thousands of times larger than the mass of the little ball. So any change that we're going to be making in terms of the mass of the little ball is so small compared to this overwhelmingly huge number for the mass of the Earth that the product's not going to change that much. So what that tells us is that on this top half of the equation, we don't have control over the universal force of gravity. We don't have control over the mass of the Earth. We do have control over the mass of the little ball, but it is so small that we're not going to make enough difference to really impact it. So that means the only thing that's left is the radius. So that's all we've got left that really is going to be an impact on this. And so let's figure out what's going on. Well, if we take a look at the radius from the center of the Earth to the center of the little ball. Okay, so there it is right there. And I'm going to leave this, and we will call that the radius. Now, if we change the string length, it basically would have the effect of either raising or lowering the height of that little ball. Not by much, but by something. And where the Earth is so large and so massive, it doesn't take much in order for that to impact what we're seeing. So if we see what happens now, we have one radius, and yes, we do have another radius. And so when we change the string length, if you see what's happening, we're literally changing the distance of the little ball from the center of the Earth. And that turns out to impact this formula. So the force of gravity on this ball is different than the force of gravity on this ball. That is a very, very simple explanation for what we're seeing, and in fact is the simplest explanation. And when we say the simplest explanation, what we're referring to is what makes sense in terms of being the easiest explanation involving the fewest number of variables that accounts for everything. I hope this explanation helps you see the two parts of the mathematical process. When we model, first we go through this brainstorming exercise where we come up with as many variables as we can. Then we have some rich discussions about why these might be effective variables. We then prune them down by first looking for variables that are actually measurable. If something's not measurable, it's not something we're going to be able to use mathematics to model with. So for example, how much I love the balls, I mean, I really love the way that looks. They're just so cool. Well, that you can't measure love. And so that's not something that's going to be an effective variable. Once that's done, then we try to find physical principles that can explain the forces or the effects we're seeing. And in this case, there was only one physical principle involved. That was the force of gravity. Fortunately for us, the force of gravity has been well explored. We understand the equation for it, and we talked our way through how to read that equation. This is important in our classes, that we help our young people be able to look at an equation and rather than just throwing their hands up in the air saying, I can't do this, to read it through and put in sensible terms. So we know the force. It's the force due to gravity. Well, that's F sub g. And big G is just a number. And we have these two masses involved, and we have these two radiuses involved. And each of these terms should be well defined. And then we work our way through the simplest explanation based on the physical principles that we understand, what we know, which are our knowns, and what we're trying to find out, which are our variables. When that's done, we come up with a lovely, lovely explanation that is based on a single variable, the length of the string. So if your group listed length of the string as one of the variables that you were working with, I think you can congratulate yourselves on that for a job well done.